Every space agency on Earth has published a Mars mission plan. Elon Musk with SpaceX wants boots on Martian soil within the decade. Animated videos show sleek spacecraft gliding toward the red planet, while astronauts float serenely through habitation modules. The presentations make it look simple: land humans, explore, return home. But here is what those animations never show you. The 17,000 individual components that must function perfectly for 900 days straight. The cascading failure chains, where one broken sensor destroys an entire mission. The mathematical reality that adding backup systems actually increases the probability of catastrophic malfunction. Scientists have run the numbers, engineers have modeled the scenarios, and the conclusion should terrify anyone who thinks we are ready. A real Mars mission does not fail because of one big problem. It collapses under the weight of 10,000 small ones happening simultaneously. If you want to understand why sending humans to Mars and bringing them home alive is the hardest engineering challenge our species will ever attempt, tap that like button and subscribe. Now, settle in and get yourself comfortable. Let's begin. Picture the most complicated machine you have ever seen. Perhaps an aircraft carrier with its 5,000 compartments, 2 nuclear reactors, and a crew of 6,000 sailors maintaining systems around the clock. Maybe a modern semiconductor fabrication plant, where robots manipulate matter at atomic scales inside clean rooms more sterile than hospital operating theatres. Perhaps the Large Hadron Collider, stretching 27 kilometers beneath the Swiss-French border, coordinating thousands of superconducting magnets cooled to temperatures colder than deep space. Now understand that a crewed Mars mission would be more complex than all of these systems combined. Operating for 3 years without external repair, without supply deliveries, without any possibility of rescue if something goes wrong. The most sophisticated machines humanity has ever built operate within a few hours of expert technicians who can diagnose problems and deliver replacement parts. A Mars spacecraft must function perfectly while its crew floats hundreds of millions of kilometers from the nearest spare component. The fantasy version of Mars exploration fits neatly into animated videos produced by space agencies and private companies competing for public attention. A rocket launches from Earth in a brilliant column of flame. Astronauts spend a few months in transit, gazing thoughtfully through portholes at the approaching red planet. They land on Mars, plant a flag in the rusty soil, collect some scientifically interesting rocks, conduct a few experiments, and fly home to ticker tape parades and congressional medals. This narrative has been repeated so often, so confidently, by so many apparently authoritative sources that most people assume the only obstacles remaining are funding and political will. Build a bigger rocket. Write a bigger check. Muster sufficient national determination. Problem solved. The reality shatters this comfortable illusion into 10,000 jagged pieces. A real mission to Mars with a planned return to Earth requires approximately 17,000 individual components working in perfect coordination across 900 days. Not 90 days like a typical International Space Station expedition, not 8 to 12 days like the Apollo lunar missions that represented humanity's furthest crewed ventures. 900 days of continuous operation in the most hostile environment humans have ever attempted to survive. 900 days. That number deserves repetition because it defines everything that follows. 2.5 years of uninterrupted system performance. 30 months where a single critical failure at any moment could cascade into mission loss. 78 weeks of thermal cycling, radiation bombardment, mechanical wear, and chemical degradation attacking every component simultaneously. Every single one of those 17,000 components exists in a web of dependencies that engineers struggle to fully map, even with the most sophisticated modeling software available. The water recycling system needs electrical power to operate its pumps and filtration membranes. The electrical system needs thermal regulation to prevent its batteries and power conditioning units from overheating in the vacuum of space where convective cooling does not exist. The thermal system needs coolant pumps circulating fluid through radiator panels. The pumps need lubricants that degrade over time when exposed to temperature extremes. The lubricant storage containers need their own temperature control to prevent the fluids from breaking down. The temperature control systems need electrical power to operate their sensors and actuators. The circle closes. Every point on that circle represents a potential mission failure, and this example traces only one simplified dependency chain among thousands that interconnect throughout the spacecraft. Engineers call this phenomenon dependency coupling. Each system connects to others in ways that multiply rather than add complexity. A spacecraft with 10 completely independent systems would have 10 possible failure points. Mission planners could address each failure mode separately, designing targeted solutions without worrying about interactions. But no real spacecraft has independent systems. A spacecraft with 10 coupled systems has potentially hundreds of failure combinations because any malfunction ripples through connected components in ways that ground testing cannot fully predict. When System A fails, it may affect Systems B, C, and D through shared power supplies. Systems B and C may have their own connections to Systems E and F. The failure propagation tree branches exponentially until mission planners face a mathematical impossibility, anticipating every possible combination of partial failures and their cascading effects. Here, we encounter the fundamental barrier that most Mars mission proposals carefully avoid mentioning. The issue is not building any single component. NASA already has life support systems that work. The International Space Station has demonstrated closed-loop water recycling and oxygen generation for over 2 decades. Private companies have built reusable rockets that land themselves on autonomous drone ships. We possess the technology to construct pressurized habitation modules, flexible spacesuits for surface exploration, and landers capable of touching down on other worlds. The components exist individually. They have been tested individually. Some have even operated in space for extended periods. What does not exist, and has never existed, is a complete integrated system that can support human life for 3 years while traveling 140 million miles from any possible help. No one has ever built such a system. No one has ever tested such a system. The first complete test will be the actual mission, with human lives depending on components that have never operated together under real conditions. Consider the mass budget problem that constrains every decision in mission architecture. Every kilogram launched from Earth's surface to Mars orbit costs approximately $1 million. When you account for the fuel required to escape Earth's gravity, the rocket structure needed to contain that fuel, the mission support infrastructure for launch operations, and the proportional cost of development amortized across limited flight opportunities. This cost relationship exists because physics imposes tyrannical constraints on rocket propulsion. Escaping Earth's gravity well requires achieving velocities exceeding 11 kilometers per second. Chemical rockets, the only proven technology for human spaceflight, accomplish this by expelling propellant at high velocities. But the propellant has mass. Lifting that propellant mass requires more propellant. The rocket equation that governs this relationship produces exponentially diminishing returns as mission requirements increase. A bare minimum human Mars mission requires landing roughly 40,000 kilograms on the Martian surface. That figure includes a pressurized habitation module, where the crew will live and work during surface operations. It includes consumables like food, water reserves, atmospheric gases, and medical supplies. It includes an ascent vehicle capable of launching from Mars and reaching orbit for rendezvous with the return spacecraft. It includes the humans themselves, along with their spacesuits, personal equipment, and the exercise machinery needed to slow physiological deterioration. 40,000 kilograms sounds manageable until you realize that this number assumes everything works perfectly on the first try, with zero margin for error or equipment redundancy. But nothing in spaceflight works perfectly on the first try. Equipment fails in ways that ground testing did not predict. Systems malfunction when exposed to conditions that simulation chambers cannot fully replicate. Components degrade faster than engineering models predicted based on laboratory evaluations. The Apollo program lost multiple spacecraft during testing before achieving successful lunar landings. Apollo 1 burned on the launch pad during a ground test, killing 3 astronauts and revealing flammability hazards that engineers had not adequately addressed. The Space Shuttle program lost 2 orbiters and 14 crew members, despite operating only in low Earth orbit, where regular maintenance and emergency return remained possible at all times. A Mars mission cannot accept these failure rates. There is no abort to Earth option once the spacecraft leaves Earth orbit. The physics of orbital mechanics commit the mission to a trajectory that cannot be reversed without propellant reserves that would themselves multiply the mass budget beyond any reasonable limit. There is no emergency resupply mission that can reach the crew in time. 9 months represents the minimum transfer time between planets during favorable orbital alignments. An emergency supply mission would require a fully fueled spacecraft sitting ready on a launch pad, which represents billions of dollars of hardware that no space agency maintains in perpetual readiness. When something breaks aboard a Mars spacecraft, the crew must fix it with whatever they brought along. They must diagnose problems without the sophisticated laboratory equipment available on Earth. They must fabricate replacement parts using limited manufacturing capabilities. They must perform repairs in cramped spaces, wearing bulky spacesuits if the affected component sits outside pressurized areas. If they cannot repair the problem, they continue the mission with degraded capability and hope the degradation does not cascade into additional failures. If the failure proves fatal, no rescue arrives. They simply die, further from home than any humans have ever died. This requirement for extreme reliability creates what engineers call the redundancy trap. The obvious solution to potential failures is backup systems. If the primary water recycler fails, switch to the backup unit. If the main flight computer crashes, activate the secondary. If the primary oxygen generator stops producing breathable air, bring the spare online. If one of the 3 main engines develops problems, the other 2 provide enough thrust to complete critical maneuvers. Each backup seems like it adds safety. Redundancy represents standard engineering practice for critical systems. Commercial aircraft carry backup hydraulic systems, backup flight computers, backup communication radios. The philosophy makes intuitive sense. More backups mean more chances for the mission to survive component failures. In reality, each backup adds complexity. And complexity is the true enemy of reliability. A single water recycling unit might have a 97% probability of functioning correctly for 900 days, based on component testing, materials analysis, and engineering models. These odds sound acceptable until you consider what 97% reliability actually means across a full mission. It means a 3% chance of failure. Across dozens of similarly critical systems, those 3% chances accumulate into near certainty that something important will break. Adding a backup water recycling unit seems like it should increase overall reliability dramatically. Now, both units would need to fail for the mission to lose water recycling capability. The mathematical probability of both independent units failing appears to be only 0.09%, calculated by multiplying 3% by 3%. But this calculation ignores a critical reality that mission architects understand, but promotional materials never mention. The backup unit is not truly independent from the primary unit. It shares power systems with the primary, drawing electricity from the same solar arrays through the same distribution network. It shares control electronics, receiving commands from the same computers through the same data buses. It shares plumbing connections, feeding processed water into the same storage tanks through the same valve assemblies. The backup requires the same maintenance procedures performed by the same crew members, using the same tools, following the same documentation. If an error exists in the maintenance checklist, both units will be maintained incorrectly. If the crew member responsible for water system maintenance becomes incapacitated, both units lose their trained operator. Any failure mode that affects the primary unit through these shared elements might simultaneously affect the backup through identical vulnerabilities. Even worse, the backup unit adds its own failure modes to the mission's total failure budget. Its valves might leak propellant from the pressurization system. Its sensors might malfunction and trigger false alarms that waste hours of crew time investigating phantom problems. Its control logic might conflict with the primary unit's operation in edge cases that testing never explored. Its physical presence in the spacecraft requires mounting hardware, access panels, and routing channels that complicate maintenance of adjacent systems. The added mass of the backup unit requires more fuel to launch from Earth, which requires larger propellant tanks, which requires stronger structural supports to handle launch stresses, which requires additional mass that requires more fuel. This spiral continues through every design iteration until the spacecraft exceeds the lift capacity of any existing or planned launch vehicle. Engineers must then find mass savings elsewhere, often by reducing backup capability in some other system, transferring risk rather than eliminating it. Aerospace engineers have a term for this phenomenon that rarely appears in public-facing mission documents. They call it complexity cascade. Every solution introduces new problems. Every backup adds new failure modes. Every additional system increases the total number of ways the mission can go catastrophically wrong, while simultaneously making the remaining systems harder to access, diagnose, and repair. The International Space Station demonstrates this reality on a smaller scale that offers sobering lessons for Mars mission planners. The station orbits Earth at an altitude of approximately 400 kilometers, close enough that resupply spacecraft arrive every few months, carrying replacement equipment, fresh food, and new crew members. Emergency evacuation to Earth requires only a few hours aboard a docked Soyuz or Crew Dragon spacecraft. Despite these advantages that no Mars mission could possibly enjoy, the station requires constant maintenance that consumes a shocking proportion of crew time. Astronauts spend approximately 2.5 hours every single day performing housekeeping and maintenance tasks just to keep the station functional. That represents more than 15% of their waking hours, devoted not to scientific research or exploration. Equipment that was designed to last 10 years often requires replacement after 3 when operating in the actual space environment, rather than the simulated conditions of ground testing. Systems that tested perfectly in thermal vacuum chambers on Earth fail within months of orbital operation due to subtle interactions between microgravity, radiation, and operational stresses that no ground facility fully replicates. The station has also experienced serious failures that would have been catastrophic for a Mars-bound crew. Ammonia leaks from cooling systems, computer failures requiring multiple reboots, oxygen generation equipment breakdowns that forced reliance on backup systems for extended periods. Each of these emergencies was resolved using resupply capability and ground support that Mars missions cannot duplicate. Mars sits at an average distance of 225 million kilometers from Earth. The actual distance varies dramatically throughout both planets' orbital periods, ranging from approximately 55 million kilometers during closest approach to over 400 million kilometers when the planets occupy opposite sides of the Sun. Mission architecture must account for these varying distances because they determine communication delays, transfer times, and abort options. At typical mission distances, radio signals traveling at the speed of light require between 4 and 24 minutes to cross the gap between planets. When mission controllers in Houston transmit a command to a Mars spacecraft, they must wait 8 to 48 minutes for confirmation that the command was received and executed. A cry for help from a crew facing an emergency would take up to half an hour to receive a response, during which time the emergency continues evolving in ways that ground controllers cannot see until the next telemetry update arrives. This communication delay eliminates one of the most powerful tools available to current space missions: real-time, ground support. When astronauts on the space station encounter a problem they cannot solve with their onboard training and documentation, they radio Houston. Engineers on the ground analyze telemetry data streaming from thousands of sensors. They run simulations on high-fidelity spacecraft models. They consult with the original equipment manufacturers. They develop step-by-step solutions tailored to the specific failure mode observed. Within hours, often within minutes for critical issues, the crew receives detailed instructions for addressing whatever problem has arisen. A Mars crew facing the same problem would send their distress message and then wait. During the wait, the problem continues evolving. A small leak becomes a larger leak. An electrical short that initially affected one system spreads to connected systems. A medical emergency that might have been treatable with immediate intervention progresses to a point where treatment options narrow. By the time Earth's solution arrives, the situation aboard the spacecraft may have changed entirely, rendering the carefully developed instructions obsolete or even counterproductive. The crew must therefore develop troubleshooting capabilities equivalent to having mission control embedded on board. This requires extensive training covering every conceivable failure scenario. It requires comprehensive documentation explaining every system in sufficient detail for field diagnosis. It requires spare parts inventories covering every component that might plausibly fail. It requires diagnostic equipment capable of isolating faults without the sophisticated laboratory instruments available on Earth. It requires manufacturing capability to fabricate replacement parts for components that were not anticipated to fail, all of which add mass, all of which add complexity, all of which add additional failure modes that themselves might require troubleshooting capabilities, that require additional mass, that adds additional complexity. The lunar missions of the Apollo era operated under fundamentally different constraints that made their achievements possible despite technology far less capable than what exists today. The Moon sits roughly 384,000 kilometers away, close enough for radio signals to complete a round trip in about 2.5 seconds. Astronauts could ask a question and receive an answer before their immediate situation changed significantly. More importantly, Apollo missions lasted only 8 to 12 days from launch to splashdown. The lunar surface stays measured in hours rather than months. Equipment needed to function reliably for only a brief period that fell well within demonstrated component lifetimes. Consumables like oxygen, water, and electrical power could be carried rather than recycled because 8 days requires finite resources that mass budgets could accommodate. The spacecraft remained essentially fresh rather than operating continuously for years before facing its most demanding operational phases. Every piece of Apollo equipment was essentially new when it launched. The command module and lunar lander had never been exposed to the thermal cycling of deep space, where temperatures swing between scorching sunlight and freezing shadow every few hours. The electronics had never experienced the cumulative radiation damage from months of exposure to solar particle events and galactic cosmic rays. The mechanical systems had never accumulated wear from thousands of operational cycles. Everything worked according to design specifications established in ground testing because nothing had yet experienced conditions that differed substantially from those ground tests. A Mars mission would place astronauts inside equipment that has already operated continuously for 9 months during the outward journey. Every SEAL has experienced thousands of thermal cycles as the spacecraft rotated between sun-facing heating and shadow-side cooling. Every electronic component has absorbed radiation damage that progressively degrades semiconductor junctions. Every mechanical system has accumulated wear that shifts tolerances and introduces play. Every chemical system has experienced reactions that slowly alter fluid properties and surface conditions. This degraded equipment must then function perfectly during the most demanding phase of the entire mission. Landing on another planet and subsequently launching back into space. The systems being called upon for peak performance will be at their lowest capability after months of environmental stress. The margins that existed when the spacecraft left Earth will have eroded precisely when the mission needs them most. This is where complexity kills. On Earth, engineers can test individual components under simulated Mars conditions. Thermal vacuum chambers expose hardware to the temperature extremes of deep space. Radiation facilities bombard electronics with particle fluxes matching solar and cosmic ray environments. Vibration tables shake assemblies to simulate launch stresses. Dust chambers contaminate mechanisms with simulants matching Martian regolith properties. What no facility on Earth can do is test everything together under realistic combined conditions for realistic mission durations. The radiation chambers cannot simultaneously provide thermal cycling. The thermal chambers cannot simultaneously provide microgravity. Each environmental factor is tested separately, and engineers hope that the combined effects do not produce unexpected interactions that individual tests fail to reveal. This testing limitation represents a fundamental barrier to Mars mission reliability that no amount of funding can eliminate. Money cannot purchase the ability to fully simulate Mars mission conditions on Earth. Technology cannot create facilities that replicate every relevant environmental factor simultaneously. Time cannot substitute for the absence of operational experience with integrated systems under actual deep space conditions. The first truly complete test of an integrated Mars mission system will occur during an actual Mars mission with actual humans aboard. Every component will be validated by exposure to conditions that cannot be fully replicated on Earth. Any design flaw that emerges from the interaction of multiple environmental stresses will manifest when the crew is hundreds of millions of kilometers from help. Any assumption that proved optimistic under ground testing will be corrected by reality when correction may no longer be possible. The Mars Curiosity rover landed in 2012 after pushing the absolute limits of current landing technology. The rover weighed 900 kilograms. A human mission would need to land 40 to 60,000 kilograms, exceeding demonstrated capability by factors of 50 or more. No technology currently exists to bridge this gap. The landing challenge alone illustrates how Mars missions differ categorically from anything humans have attempted. The entry sequence offers zero margin for error. Unlike orbital operations where a malfunctioning spacecraft can often be stabilized and evaluated, an entry trajectory commits the vehicle to either a successful landing or a fatal crash. There are no abort options once the spacecraft enters the Martian atmosphere. Every system must work correctly the first time it is called upon, using equipment that has degraded for 9 months in the deep space environment. An entry trajectory commits the vehicle irreversibly. Once the spacecraft begins atmospheric interface, it will either land successfully or crash. There are no abort modes that return the vehicle to space. There are no holds while teams troubleshoot unexpected readings. Every system must work correctly the first time it is called upon, using components that have degraded for months, executing procedures that have never been tested in actual conditions, while human lives depend on every valve, sensor, and computation performing exactly as designed. And here again, we encounter the central obstacle that pervades every aspect of Mars mission planning. We are not attempting to solve a single engineering challenge where success in one domain provides foundation for addressing the next challenge. We are attempting to solve thousands of challenges simultaneously, and each solution we develop for one problem creates new problems in adjacent systems that require their own solutions that create their own adjacent problems. The Mars mission that appears in promotional videos represents a fantasy constructed by ignoring dependency chains, testing limitations, complexity mathematics, and the accumulated lessons of every previous human spaceflight program. The animations show astronauts smiling confidently as they float through pristine modules. The reality would involve exhausted crews performing constant maintenance on degrading systems while troubleshooting failures that ground testing failed to anticipate. A real human mission to Mars with a planned return to Earth would require either accepting failure, probabilities that no government could politically survive should the mission end in crew loss, or reducing mission complexity to levels that eliminate most of the scientific value used to justify the enormous expense in the first place. This is the trap that Mars mission planners cannot escape through better engineering, more funding, or greater determination. The trap is built into the physics of interplanetary distances, the chemistry of life support requirements, and the mathematics of system reliability over extended operations. But complexity in transit represents only the first challenge. What happens when the crew must actually survive aboard this intricate web of interdependent systems is far worse. The life support requirements for keeping humans alive reveal dependency chains that make propulsion and navigation look simple by comparison. The human body is spectacularly unsuited for space travel. Evolution designed us for a very specific environment. The surface of a planet with breathable atmosphere, moderate temperatures, abundant liquid water, and a magnetic field that deflects most cosmic radiation. Remove any one of these conditions and the human body begins dying within minutes to hours. Remove all of them simultaneously, as space travel does. And survival requires recreating Earth's environment inside a metal container while hurtling through the most hostile vacuum imaginable. This biological reality forms the foundation of every complexity problem in crewed Mars missions. Keeping humans alive requires systems that keeping cargo alive does not. A robot can sit in a powered-down state for 9 months, activate upon arrival, and function perfectly regardless of temperature fluctuations or radiation exposure during transit. A human needs to breathe every few seconds, drink every few hours, eat every few days, sleep every night, exercise every day, maintain psychological stability across every moment of a 3-year journey through absolute emptiness. The life support system required for a Mars mission represents the most complex integrated engineering challenge in human history. Not because any individual component is impossible to build, NASA and its international partners have developed life support technology over 6 decades of human spaceflight. The challenge exists because every component connects to every other component in ways that multiply failure modes exponentially rather than adding them linearly. Start with the most basic requirement: breathable air. Humans consume approximately 700 to 800 liters of oxygen per day through normal respiration, with rates increasing during physical activity. A crew of 4 would need roughly 3,000 liters daily. Across a 900-day mission, a 4-person crew would consume nearly 3 million liters of oxygen. 6 crew members would require almost 4.5 million liters. Carrying this much gas in pressurized tanks would require mass that no rocket can lift. At standard temperature and pressure, 3 million liters of oxygen weighs approximately 4,300 kilograms. The tanks required to store this gas at safe pressures would weigh several times more than the gas itself. The structural support required to secure these tanks during launch acceleration would add additional mass. The total oxygen storage mass for a minimal crew would exceed 15,000 kilograms before accounting for the inevitable losses from airlock cycling, small leaks, and emergency reserves. This single consumable would consume a substantial fraction of the entire mission's mass budget, leaving insufficient capacity for food, water, equipment, and the crew themselves. The solution is regeneration. The environmental control and life support system must produce oxygen from available resources rather than carrying the mission's entire supply from Earth. This approach trades stored consumables for mechanical systems that generate consumables continuously. The trade appears favorable on paper, but introduces complexity that stored supplies avoid. Current technology accomplishes oxygen regeneration through electrolysis of water, using electrical current to split H2O molecules into hydrogen gas and breathable oxygen. The International Space Station employs this approach, operating the oxygen generation system that has produced breathable air for crew members since 2007. The system works. It has been validated through years of operational experience. But the station's oxygen generation system receives water from cargo resupply missions that arrive every few months. The system does not need to recycle every molecule because fresh supplies arrive regularly. When components fail, replacement parts arrive on the next cargo vehicle. When performance degrades, technicians on Earth analyze telemetry data and develop solutions that crew members implement with ground support available in real time. A Mars mission cannot receive cargo resupply. Every drop of water used for oxygen production must either be brought from Earth at enormous mass cost or recovered from crew waste through recycling systems that introduce their own complexity chains. This closed-loop requirement transforms a manageable engineering problem into an interconnected web of dependencies where any single failure can cascade through the entire life support architecture. Water recycling systems collect moisture from multiple sources throughout the spacecraft. Humidity from crew respiration condenses on cooling surfaces and drains into collection tanks. Perspiration evaporates from skin and clothing, joining the atmospheric moisture that the dehumidification system captures. Urine passes through processing systems that extract water while concentrating waste products for storage or disposal. Even moisture from food preparation and consumption enters the recycling stream. This collected water carries contaminants that must be removed before the water can be consumed or electrolyzed for oxygen production. Organic compounds from biological waste require filtration through activated charcoal beds that absorb contaminants through chemical binding. Dissolved minerals from sweat and urine require processing through ion exchange resins that capture charged particles. Bacterial contamination requires treatment through ultraviolet sterilization or chemical disinfection that kills microorganisms without introducing toxic residues. Each purification stage requires its own equipment with its own failure modes. The activated charcoal beds become saturated over time and must be regenerated through heating cycles or replaced from stored spares. The ion exchange resins require periodic regeneration, using acids and bases that must be stored safely and handled carefully. The ultraviolet lamps degrade with use, losing sterilization effectiveness unless replaced according to maintenance schedules. The purified water then feeds into electrolysis units that generate oxygen while simultaneously producing hydrogen gas as a byproduct. The electrolysis cells require precise electrical current and voltage to operate efficiently. They require pure water because mineral contamination coats electrode surfaces and reduces performance. They require temperature control because efficiency varies with operating conditions. They require pressure management because the gases produced must be separated and directed to appropriate systems. The hydrogen, produced by electrolysis, presents its own challenge that mission planners cannot ignore. Venting hydrogen into the spacecraft cabin creates explosion risk because hydrogen mixed with oxygen becomes violently combustible when exposed to ignition sources. The concentration required for explosion is surprisingly low. Hydrogen becomes dangerous at concentrations as low as 4% in air. A small electrolysis malfunction that released hydrogen into the cabin atmosphere could create conditions for catastrophic fire or explosion. Dumping hydrogen overboard into space eliminates the explosion hazard, but wastes mass that originally came from precious water supplies. Every hydrogen molecule vented represents water that cannot be recovered, slowly depleting the closed-loop system that the mission depends upon. Over 900 days, these losses accumulate into significant water deficits that must be covered by reserves carried from Earth or by accepting progressively degraded margins. Current mission designs propose combining the waste hydrogen with carbon dioxide scrubbed from cabin air, producing methane and water through a chemical process called the Sabatier reaction. This approach recovers water that would otherwise be lost while simultaneously disposing of carbon dioxide that must be removed from the atmosphere anyway. The elegance of this solution masks the complexity it introduces. Notice what has happened through these sequential design decisions. Oxygen generation now depends on water recycling, providing purified feedstock. Water recycling depends on carbon dioxide scrubbing, providing the CO2 required for the Sabatier reaction. Carbon dioxide scrubbing depends on air circulation, moving cabin atmosphere through the scrubbing beds. Air circulation depends on fan motors that require electrical power to operate continuously. The electrical system depends on solar panels during the cruise phase, converting sunlight into electricity through photovoltaic cells that degrade slowly from radiation exposure. During surface operations, when dust storms may block sunlight for weeks, power generation might require nuclear reactors using radioisotope thermoelectric generators or fission systems that have never been qualified for human life support applications. Each power system requires thermal management to prevent overheating in vacuum, where convective cooling does not occur. On Earth, hot electronics shed heat to surrounding air through convection currents. In space, the only heat rejection mechanism is radiation. Surfaces must be maintained at carefully controlled temperatures to radiate waste heat at rates that balance internal heat generation. Thermal management systems pump coolant through networks of tubes and radiator panels that shed excess heat to space through infrared radiation. The pumps require electrical power and mechanical seals that can wear out from continuous operation. The coolant fluid degrades over time from radiation exposure and chemical breakdown. The radiator panels are exposed to micrometeorite bombardment that can puncture cooling lines and release coolant into space. A coolant leak in the thermal management system cascades into overheating of electrical components that the cooling loop serves. Overheating electronics fail or shut down through protective circuits. Failed or shut down electronics remove power from life support systems that depend on them. Life support systems without power stop processing air, water, and waste. Crew members begin dying within hours from carbon dioxide buildup, dehydration, or thermal stress depending on which system fails first. This brings us back to the real problem that makes life support fundamentally different from other engineering domains. The systems are not merely complex. They are coupled in ways that create failure cascades impossible to fully anticipate. Testing individual components reveals individual failure modes. Testing subsystems reveals subsystem failure modes. But the emergent failure modes that arise from interactions between dozens of subsystems operating simultaneously for years cannot be discovered through ground testing. They reveal themselves only during actual operations, when the crew has no option except to respond or die. Consider the carbon dioxide scrubbing process in detail, because it illustrates how simple-sounding requirements generate tremendous complexity when examined closely. Humans exhale approximately 1 kilogram of carbon dioxide daily through normal respiration. A 4-person crew generates 4 to 6 kilograms of carbon dioxide daily, depending on activity levels. Carbon dioxide toxicity occurs at concentrations far lower than most people realize. At concentrations above 1%, roughly 10 times normal atmospheric levels, some individuals begin experiencing headaches and reduced cognitive function. At 3%, nearly everyone experiences headaches, dizziness, and impaired judgment that affects task performance. At 5%, confusion and loss of consciousness occur. At 8%, death follows within minutes. The spacecraft cabin atmosphere must maintain carbon dioxide levels below 1% continuously for 900 days. Any interruption in scrubbing capability, any reduction in processing rate, any malfunction that allows carbon dioxide to accumulate creates conditions that degrade crew performance and potentially kill crew members before they can implement corrective actions. The International Space Station removes carbon dioxide using beds of zeolite minerals that absorb the gas from cabin air through chemical adsorption. Zeolite crystals contain molecular-scale cavities that trap carbon dioxide molecules while allowing oxygen and nitrogen to pass through. The beds saturate over time as the cavities fill with absorbed gas. Regeneration exposes the saturated beds to vacuum, causing the trapped carbon dioxide to release into space while restoring the bed's absorption capacity. This system requires continuous electrical power to operate blowers that move cabin air through the zeolite beds at flow rates sufficient for adequate carbon dioxide removal. It requires heaters to warm the beds during regeneration cycles Because warmer temperatures accelerate gas release, it requires valves that seal properly under repeated cycling between cabin pressure and vacuum. It requires sensors that accurately measure carbon dioxide concentrations throughout the cabin volume. Over 900 days, the valves controlling vacuum exposure will actuate approximately 100,000 times. Each actuation stresses valve seats, flexes sealing surfaces, and cycles materials through temperature gradients as warm cabin air contacts cold vacuum-exposed surfaces. Mechanical components that function perfectly during ground testing sometimes fail after 10,000 cycles due to fatigue mechanisms that accelerate in the space environment. The valve manufacturers can provide reliability data based on accelerated lifetime testing, where components are cycled rapidly under controlled conditions to simulate extended operation. But no ground test replicates the combined environment of deep space. The radiation that embrittles polymers and degrades lubricants, the microgravity that changes fluid behavior and particle settling, the thermal cycling between solar heating and shadow cooling, the vibration from crew activity and equipment operation. The reliability data provides estimates that actual operations may not confirm. The Mars Mission Planner's solution follows standard engineering practice. Backup systems carry 2 complete carbon dioxide scrubbing units. If the primary unit fails, activate the secondary. This approach works for the space station, which has deployed backup systems when primary equipment failed and then received replacement parts through subsequent resupply missions. But backup systems create their own complexity burden that erodes the reliability improvement they were intended to provide. The backup unit requires storage space, which increases spacecraft interior volume, which increases the structural shell area that must withstand pressure loads, which increases structural mass. The backup requires installation hardware, including mounting brackets, plumbing connections, and electrical interfaces, each of which adds potential leak paths and failure points. The backup requires crew training for activation procedures, adding content to already packed pre-mission training schedules, where every hour of instruction competes with other essential skills. The backup requires diagnostic systems to determine when primary equipment is actually failing versus when sensors are providing false readings that do not warrant backup deployment. The diagnostic systems themselves require maintenance and calibration. False alarms consume mission resources even when nothing is actually wrong. If a carbon dioxide sensor incorrectly indicates dangerous concentration levels due to calibration drift, electrical noise, or sensor degradation, the crew must respond as though a real emergency exists. Standard emergency protocols might require evacuating a module, donning protective breathing equipment, or initiating backup system activation. Each false alarm burns crew time that could be spent on other tasks. It depletes emergency supplies that might be needed for actual emergencies. It accumulates psychological stress that degrades crew performance over subsequent weeks and months. The psychological dimension of life support extends far beyond merely keeping the body physically alive. Human minds require inputs and outputs that spacecraft cannot easily provide. Isolation studies conducted on Earth in facilities designed to simulate long-duration space missions demonstrate that healthy individuals begin showing psychological deterioration after approximately 4 to 6 months of confinement with a small group. These deterioration patterns manifest differently across individuals but follow recognizable trajectories. Sleep disturbances appear first as circadian rhythms drift without natural day-night cues. Irritability increases as minor interpersonal frictions accumulate without the release valves that normal social life provides. Motivation decreases as tasks become repetitive, and accomplishment feels disconnected from meaningful outcomes. Depression emerges as the weight of isolation presses on minds evolved for rich social environments. A Mars mission would confine 4 to 6 people in a pressurized volume smaller than a typical house for roughly 30 months. The habitation module designs that fit within mass constraints provide approximately 100 cubic meters of pressurized space per crew member. This sounds generous until you realize that the same volume must contain equipment, storage, workstations, exercise facilities, food preparation areas, and personal sleeping quarters. The effective living space available to each crew member amounts to perhaps 20 cubic meters of accessible volume, roughly equivalent to a modest bedroom. This space must serve all functions: sleeping, working, exercising, relaxing, eating, and the limited personal activities possible in such an environment. There is no privacy except through headphones and closed eyes. There is no solitude except during sleep periods when other crew members occupy the same module. The crew cannot step outside for fresh air, because outside the spacecraft hull exists only vacuum and radiation. They cannot take a walk to clear their heads because the walking distance available consists of a few dozen meters of corridor. They cannot video chat with family and friends without round-trip communication delays, measured in minutes to tens of minutes depending on planetary positions. The delay makes natural conversation impossible, transforming video calls into exchanges of recorded messages that lack the responsive flow of normal human interaction. They cannot receive visits from friends, therapists, managers, or anyone who is not already aboard the spacecraft. Every interpersonal conflict, every personality friction, every accumulating resentment will occur within the same confined space where the crew must also perform safety-critical tasks, maintain life-sustaining equipment, and respond to emergencies that may require split-second coordination. Ground-based Mars simulation studies conducted in isolated facilities have documented conflict escalation patterns that should concern mission planners. Minor disagreements about task allocation or scheduling amplify over months of confinement as participants lack outlets for frustration. Communication breaks down as crew members begin avoiding interactions with individuals who irritate them. Passive-aggressive behaviors replace direct confrontation, as confined individuals seek to express frustration without triggering open conflict. In the most severe cases documented in simulation studies, participants have refused to speak to each other for extended periods, communicating only through written notes or third-party intermediaries. In those simulations, affected individuals retained the option to leave if conditions became truly intolerable. Mission rules permitted early termination for psychological reasons. Medical staff monitored participant welfare and could intervene if safety concerns arose. On an actual Mars mission, there is no exit. The crew cannot leave, they cannot be removed, they cannot be replaced. They must continue functioning as a team, regardless of interpersonal dynamics, because their individual survival depends on coordinated responses to the emergencies that will inevitably occur. A crew fractured by psychological conflict faces equipment failures with degraded teamwork, communication, and mutual trust. Psychological breakdown during a mission creates life support challenges that no amount of redundant hardware can address. A crew member who refuses to perform assigned maintenance tasks forces others to absorb additional workload during shifts that were already filled with essential activities. The affected individual's maintenance assignments do not disappear. The cascading effects spread through mission operations in ways that hardware redundancy cannot prevent. A crew member experiencing paranoid episodes might interpret normal equipment sounds as evidence of conspiracy or sabotage. They might refuse to trust information provided by other crew members. They might take actions intended to protect themselves that actually damage spacecraft systems or endanger others. A crew member who becomes violent poses direct risks to other crew members and to spacecraft integrity. Mental health intervention options during a Mars mission are extremely limited compared to terrestrial resources. Psychiatric medications exist that can treat various psychological conditions, but these medications have side effects that may impair task performance. Sedatives that calm an agitated individual also slow their reflexes and cloud their judgment, potentially rendering them unable to respond appropriately to emergencies. Antidepressants and antipsychotics require weeks to reach therapeutic effectiveness, providing no rapid response to acute episodes. Sedation removes a trained crew member from the active roster, shifting their responsibilities to others who must somehow absorb additional workload without any increase in available time or energy. The sedated individual cannot perform maintenance. They cannot respond to emergencies, they cannot contribute to problem solving. The effective crew size decreases while the mission demands remain constant. There is no possibility of evacuation to Earth for psychiatric treatment, regardless of how severe conditions become. The mission must either continue with a compromised crew member or abort entirely, assuming abort options even exist at the relevant mission phase. During certain portions of the trajectory, the physics of orbital mechanics commit the spacecraft to completing its journey regardless of crew condition, which circles back to the underlying constraint that infects every proposed solution to life support challenges. The human body and mind create requirements that drive system complexity far beyond what robotic missions require. Every additional system added to address human needs creates new failure modes that did not exist before. The mission design spirals toward either unacceptable complexity that mathematics says will fail, or unacceptable risk that ethics says cannot be accepted. Consider medical emergencies beyond psychological conditions. Appendicitis occurs in approximately 100 people per 100,000 per year in the general population. This rate varies with age and other factors, but healthy adults selected for space missions fall within typical ranges. Across a 6-person crew over a 30-month mission, the probability of at least one appendicitis case approaches 2%. 2% sounds low until you consider how many similar low-probability events could occur: kidney stones, gallbladder attacks, cardiac arrhythmias, strokes, deep vein thrombosis, herniated discs, severe dental emergencies, eye injuries, and hundreds of other conditions each have their own occurrence rates. The compound probability of at least one serious medical emergency across a multi-year mission with multiple crew members approaches certainty. On Earth, appendicitis is treated by surgical removal within hours of diagnosis. The procedure is routine, performed thousands of times daily in hospitals worldwide. Untreated appendicitis progresses through predictable stages. Inflammation causes worsening pain. The appendix wall weakens. Rupture releases bacteria into the abdominal cavity. Peritonitis develops as infection spreads. Sepsis occurs as bacteria enter the bloodstream, and death follows within days without intervention. A Mars spacecraft cannot carry a fully equipped surgical suite with the sterile environment, anesthesia equipment, and post-operative care facilities that appendectomy requires. The mass budget cannot accommodate an operating theatre. The training time cannot include surgical residency. The staffing cannot include multiple surgeons who can operate on each other if needed. The proposed solution for appendicitis specifically is pre-mission appendectomy for all crew members, removing the organ before launch so it cannot cause problems during the mission. This approach eliminates appendicitis risk, but does not address the hundreds of other conditions that cannot be prevented through prophylactic surgery. The crew physician faces impossible constraints when medical emergencies occur. They must diagnose conditions using portable equipment with capabilities far below terrestrial hospital standards. Handheld ultrasound devices provide some imaging capability, but lack the resolution and clarity of hospital equipment. Blood analysis requires consumable test supplies that cannot be restocked. Diagnostic algorithms depend on training that cannot cover every possible presentation of every possible condition. They must treat conditions using medications that have degraded during months of radiation exposure. Pharmaceutical compounds break down over time, even under controlled storage conditions. Radiation accelerates this degradation through mechanisms that standard shelf life testing does not account for. A drug that maintains 90% potency after 2 years of room temperature storage might retain only 60% potency after 9 months of space radiation exposure. They must perform procedures in microgravity, where blood and other fluids do not behave as they do on Earth. Blood does not pool at the lowest point of a wound. It forms floating spheres that can obscure the surgical field and contaminate nearby surfaces. Irrigation fluids spray unpredictably. Instruments must be tethered, or they drift away. The physician must work in conditions that fundamentally differ from every training scenario they experienced. They must manage post-treatment recovery in an environment where the patient cannot simply rest in bed. There are no beds in microgravity, only restraint systems that hold sleeping crew members in place. The recovering patient cannot avoid movement because daily exercise is mandatory to prevent further physiological deterioration. They cannot remain isolated because the spacecraft lacks space for dedicated medical wards. Every medical intervention also depletes supplies that cannot be replaced from any source. Antibiotics used for one infection are not available for subsequent infections that might occur in other crew members. Painkillers administered for one injury reduce stocks available for future injuries. Surgical supplies consumed in one procedure leave less capability for later emergencies. The mission must carry enough medical supplies to handle multiple simultaneous medical events, while also carrying backup supplies in case primary stocks are damaged, contaminated, or lost to equipment failures. Yet even addressing all of these medical concerns falls short, because the medical challenge cannot be separated from other mission systems. A crew member recovering from surgery cannot perform their assigned maintenance duties. Someone else must cover those tasks while also managing their own responsibilities. The additional workload increases stress on the healthy crew members. Stress increases probability of errors. Errors during maintenance could damage life support equipment. Life support damage threatens the entire crew, including the patient who needed surgery in the first place. Bone density loss in microgravity proceeds at approximately 1 to 2% per month, despite countermeasures like resistance exercise that mission plans include. Across the 9-month transit to Mars, crew members would lose 10 to 15% of their bone mass, regardless of how diligently they follow exercise protocols. This degradation increases fracture risk during surface operations where crew members will walk, climb, and work in pressure suits. A broken bone on Mars creates medical challenges that dwarf anything the same injury would create on Earth. Muscle atrophy accompanies bone loss through mechanisms that exercise only partially counteracts. Even with mandatory exercise protocols requiring 2 hours daily, astronauts returning from 6-month space station missions require weeks of rehabilitation before resuming normal physical activities. They experience difficulty standing, walking, and maintaining balance as their bodies readapt to Earth gravity. A Mars crew would arrive at their destination after 9 months of physiological degradation, then immediately face the most demanding physical activities of the entire mission. Surface exploration in bulky pressure suits that restrict movement and impose their own physical demands. The exercise equipment required to slow physiological deterioration adds mass, volume, and mechanical complexity to the spacecraft. Treadmills, resistance machines, and cycle ergometers each require maintenance, spare parts, and crew time for operation. They consume electrical power that competes with other systems. They take up interior volume that could otherwise house backup equipment or additional supplies. Radiation exposure accumulates throughout the mission regardless of crew activities. Deep space contains energetic particles from 2 primary sources: solar particle events that occur unpredictably when the Sun ejects high-energy protons during flares and coronal mass ejections, and galactic cosmic rays that originate from beyond the solar system and arrive continuously from all directions. The International Space Station receives partial protection from Earth's magnetic field, which deflects many charged particles before they reach the station's orbital altitude. A Mars-bound spacecraft would operate entirely outside this magnetic shield from the moment it leaves low Earth orbit. The crew would receive the full unshielded dose of both solar and galactic radiation throughout the mission. Current estimates suggest a round-trip Mars mission would expose crew members to radiation doses approaching or exceeding 1 sievert, roughly equivalent to 10,000 chest X-rays or more distributed across the mission duration. This exposure increases lifetime cancer risk by approximately 5% above baseline rates, exceeding the limits that NASA has established for astronaut radiation exposure during their careers. Either those limits must be waived, accepting increased cancer risk as a cost of exploration, or the mission must carry radiation shielding mass that displaces other essential cargo. Neither option is attractive. Waiving safety limits exposes the agency to liability and ethical criticism. Carrying shielding mass reduces capability for every other mission system. Effective radiation shielding requires substantial mass because the physical mechanism of shielding involves absorbing particle energy through collisions with atomic nuclei. More mass means more atoms available for collisions, means more energy absorption, means better protection. There are no clever engineering shortcuts that provide shielding without mass. Water provides reasonable radiation protection and serves double duty as consumable supply that the mission must carry anyway. Surrounding the crew habitat with water tanks creates shielding while storing resources the crew needs for survival. But water has mass that must be launched from Earth at enormous cost. The quantity required for meaningful shielding, perhaps 10 to 15 centimeters of water surrounding crew sleeping areas, would add thousands of kilograms to mission mass requirements. Hydrogen-rich materials like polyethylene provide better shielding per kilogram than water because hydrogen atoms are particularly effective at absorbing proton energy. But polyethylene is flammable in oxygen-rich atmospheres, creating fire risk inside the spacecraft. Fire aboard a sealed spacecraft is among the most dangerous emergencies possible. The Apollo 1 tragedy demonstrated this risk with fatal clarity. 3 astronauts died when fire swept through their command module during a ground test. Burning in an atmosphere of pure oxygen at slightly above sea level pressure, the fire spread so rapidly that the crew could not open the hatch before succumbing to smoke and burns. Investigation revealed that the pure oxygen atmosphere created conditions where materials that would not burn in normal air became intensely flammable. Modern spacecraft use mixed atmospheres with lower oxygen concentrations to reduce fire risk, but any atmosphere that supports human respiration contains enough oxygen to support combustion of suitable materials. Fire suppression systems require their own mass budget, complexity burden, and maintenance procedures. The suppression agents must extinguish flames without damaging sensitive electronics, poisoning the crew through toxic decomposition products, or depleting the atmosphere to unbreathable oxygen levels. They must activate reliably after years of storage, during which the suppression agent containers experience the same radiation, thermal cycling, and vibration that affects every other component. They must function effectively in microgravity, where flames behave differently than on Earth. Without convection currents to carry hot gases upward and draw fresh oxygen from below, flames in microgravity form spherical shapes and can burn in unexpected directions. The interconnection of challenges continues to multiply with each additional factor considered. It is dozens of subsystems that must all function simultaneously and continuously for 30 months. Every component depends on other components, through power, thermal, data, and physical connections. Every backup system added to improve reliability introduces new dependencies that link systems together in ways that create new failure cascades. Every human occupant of the spacecraft adds requirements that drive complexity higher. Each person consumes oxygen, produces carbon dioxide, requires water, generates waste, occupies volume, demands exercise equipment, needs medical supplies, and brings psychological vulnerabilities that can affect the entire crew. Adding more crew members to improve redundancy of human skills simultaneously increases consumption rates, waste generation, interpersonal conflict potential, and medical emergency probability. The life support paradox encapsulates the entire Mars mission challenge in miniature. The International Space Station has demonstrated this capability repeatedly over more than 2 decades of continuous human presence. Astronauts have remained healthy and productive during 6-month expeditions and even year-long missions, but the station operates with constant resupply that replaces consumables and provides spare parts. It operates with regular crew rotation that limits individual exposure to space environment effects. It operates with the possibility of emergency evacuation that provides a safety net for conditions that cannot be managed in orbit. It operates within Earth's magnetic field, which provides partial radiation protection unavailable to Mars-bound spacecraft. Remove those safety nets, extend the mission duration by a factor of 5. Place the spacecraft so far from Earth that resupply is impossible and evacuation cannot happen. Expose the crew to radiation levels that exceed anything station astronauts experience. The mathematics of reliability produce numbers that should give everyone pause. A system with 99% reliability over 6 months has approximately 94% reliability over 30 months because failure probability accumulates over time. A spacecraft with 100 such systems would have a compound reliability below 2% because each system's reliability multiplies together. Even 99.9% reliable components, integrated across thousands of elements over 30 months, produce mission failure probabilities that engineers prefer not to discuss during public presentations about Mars exploration timelines. This is why no nation has committed actual flight hardware to a crewed Mars mission, despite decades of studies, proposals, and announcement ceremonies. The engineering of individual components is theoretically possible with current or near-term technology. The reliability mathematics of integrated systems operating for mission durations are not favorable regardless of how much funding or political will exists. But even if the transit somehow succeeded, the crew would then face the most dangerous phases of the entire mission: landing on Mars, surviving on the surface, and launching back into space using equipment that has been degrading since it left Earth. Landing on Mars does not represent the triumphant conclusion of mission risk. It marks the beginning of the most dangerous operational phase, where system complexity reaches its absolute maximum while the crew remains maximally distant from any possible assistance. Everything that can go wrong during the 9-month transit can also go wrong on the Martian surface, but surface operations introduce entirely new categories of failure that exist only on an alien world with conditions no human has ever directly experienced. The popular imagination pictures the landing as the climactic moment. The spacecraft touches down, the crew opens the hatch, and the first human footprints appear in Martian soil. In this narrative, landing equals success. The mission has arrived. The hard part is over. The engineering reality inverts this comfortable assumption completely. Landing represents the moment when mission complexity explodes to levels that dwarf transit operations. The crew must now operate equipment that has been deteriorating for 9 months, in an environment that ground testing cannot fully simulate, while attempting activities that humans have never performed, using systems that have never been validated under actual conditions. The landing itself presents challenges that dwarf anything attempted in human spaceflight history. The Apollo lunar module descended through pure vacuum, using only rocket thrust to slow its approach to the lunar surface. There was no atmosphere to complicate entry dynamics. The descent engine fired, the spacecraft slowed, the landing legs touched down. The physics were straightforward, even if the execution required extraordinary precision. Mars has an atmosphere. This seems helpful at first consideration because atmospheric drag could slow a descending spacecraft without consuming propellant. Earth landings rely heavily on atmospheric braking, with parachutes and aerodynamic surfaces doing most of the deceleration work before final propulsive touchdown. Perhaps Mars landings could follow similar approaches. The numbers destroy this hope. Martian air is thick enough to generate destructive aerodynamic heating during entry at interplanetary velocities. A spacecraft arriving from Earth hits the Martian atmosphere at approximately 20,000 kilometers per hour. At this velocity, atmospheric compression creates temperatures exceeding 1,000 degrees Celsius on forward-facing surfaces. The heat shield must absorb this thermal assault while protecting the crew and cargo behind it. But the same atmosphere that generates dangerous heating is too thin to slow a human-scale lander through parachute deployment alone. Mars' surface pressure averages about 600 pascals, roughly 0.6% of 1% of Earth's sea level pressure. A parachute that would gently lower a payload on Earth provides almost no deceleration on Mars. The air simply lacks the density to generate adequate drag forces against parachute canopies. Current Mars landing technology maxes out at approximately 1 metric ton of payload delivered to the surface. The Curiosity rover, weighing 900 kilograms, pushed this limit to its absolute boundary. Landing Curiosity required an entirely new entry system called the Sky Crane, where a rocket-powered descent stage lowered the rover on cables before flying away to crash at a safe distance. This system had never been tested under actual Mars conditions before the mission. Every component worked on the first and only attempt that mattered. Engineers at the Jet Propulsion Laboratory watched in controlled horror during Curiosity's 7-minute entry sequence, knowing that a single component failure among thousands would destroy the rover before it could return a single byte of scientific data. The communication delay meant that by the time entry telemetry reached Earth, the landing had already succeeded or failed. Mission controllers could only watch historical data, describing events that had concluded minutes earlier. The Perseverance rover landing in 2021 used similar technology with incremental improvements. Again, the system worked perfectly on its single opportunity, but both rovers represent the upper mass limit of current landing capability. A human mission would need to deliver 40 to 60 metric tons to the Martian surface, a factor of 40 to 60 beyond demonstrated technology. No technology currently exists to accomplish this delivery. The gap between 1 metric ton and 50 metric tons is not an incremental engineering challenge that additional funding could close. It represents a fundamental capability boundary that requires entirely new approaches to entry, descent, and landing systems. Proposed solutions involve combinations of aerodynamic deceleration using inflatable heat shields that expand the vehicle's cross-section, supersonic retropropulsion, where rocket engines ignite while the vehicle still travels faster than sound, and precision guidance systems that navigate through dynamic atmospheric conditions while managing propellant consumption against deceleration requirements. No integrated system combining these technologies has ever been built, tested, or flown. The first complete test would occur during an actual crewed landing attempt. The entry trajectory offers zero margin for navigation error in ways that ground controllers cannot fully appreciate until they examine the orbital mechanics. A spacecraft approaching Mars at interplanetary velocities must hit an entry corridor approximately 10 kilometers wide, measured at the point where atmospheric effects begin. 10 kilometers sounds like a generous target until you consider the context. The spacecraft has been traveling for 9 months across distances measured in hundreds of millions of kilometers. Throughout this journey, navigation has relied on ground-based tracking that measures position and velocity through radio signals. Small errors in these measurements accumulate over the transit duration. Solar radiation pressure, gravitational perturbations from other planets, and outgassing from spacecraft surfaces create trajectory deviations that ground controllers estimate but cannot directly measure. By the time the spacecraft approaches Mars, its actual position may differ from its calculated position by tens of kilometers. Course correction maneuvers during the final approach can reduce this uncertainty, but propellant limitations constrain how much correction is possible. The entry corridor must be hit despite residual navigation errors that exceed the corridor width in worst-case scenarios. Miss high, and the vehicle skips off the upper atmosphere like a stone bouncing off water. The spacecraft continues past Mars on a trajectory that cannot be corrected because the propellant budget assumed successful capture, not a second approach attempt. The crew watches Mars recede in their windows as their life support consumables tick down toward exhaustion, miss low, and the vehicle plunges too steeply into the atmosphere. The descent angle increases aerodynamic heating beyond what the heat shield can survive. Structural failure occurs at hypersonic velocities, scattering debris across hundreds of kilometers of Martian terrain. The crew dies before they understand what happened. The corridor must be threaded after 9 months of accumulated navigation uncertainty, using systems that have degraded since launch, by a guidance computer running software that has never been tested under actual Mars approach conditions. Ground controllers can provide trajectory updates, but cannot intervene in real time due to communication delays. The spacecraft must navigate its own entry autonomously, making decisions based on sensor inputs that may or may not accurately reflect actual conditions. Assuming successful atmospheric entry through the narrow corridor at acceptable angles, the landing sequence must reduce velocity from approximately 20,000 km per hour to zero in roughly 7 minutes. This deceleration timeline is dictated by the geometry of Mars entry, not by mission planners who might prefer a more gradual approach. The thin atmosphere provides less drag than Earth's during the critical deceleration phase. Even with the largest feasible heat shields and parachutes, a human-scale lander would still be traveling at several hundred meters per second when atmospheric braking reaches its practical limit. The remaining velocity must be cancelled through propulsive deceleration, rocket engines burning propellant to slow the vehicle for touchdown. This propellant mass required for terminal deceleration must be carried from Earth through the entire 9-month transit, then protected through atmospheric entry heating, then fed to engines that must ignite reliably after months of storage and the violence of entry dynamics. The propellant feed systems include valves, pumps, filters, and pressurization systems, each with their own failure modes that manifest only under actual operational conditions. Landing site selection constrains mission architecture in ways that propagate through every subsequent system design decision. Scientifically interesting locations on Mars tend to occupy terrain that is dangerous for landing. Crater rims offer geological diversity and access to layered rock formations that record planetary history. Valley walls expose cross-sections through ancient sedimentary deposits. Boulder fields mark locations where water once flowed with enough force to transport rocks across the landscape. All of these features create landing hazards that could destroy a spacecraft during touchdown. Slopes destabilize landed vehicles, boulders puncture landing legs or tip vehicles onto their sides. Loose sediments cannot support vehicle weight, causing landing pads to sink into soil that ground testing could not adequately simulate. Safe landing sites tend to be flat, featureless plains with limited scientific value. The smooth terrain that makes touchdown survivable often indicates geological uniformity that reduces exploration interest. The mission must balance exploration objectives against survival requirements, typically by compromising both. The crew lands somewhere moderately safe with moderate scientific interest, satisfying neither the engineers who want maximum margins nor the scientists who want access to the most revealing terrain. The touchdown moment presents its own failure modes, independent of entry and descent systems. These legs have been folded in storage configuration for 9 months, experiencing thermal cycling that affects their deployment mechanisms and structural properties. They must deploy correctly, lock into position securely, and survive ground contact loads without buckling. The surface beneath the landing site must support the vehicle mass without giving way. Mars rovers have occasionally experienced wheel slippage in loose soil that trapped vehicles for extended periods. A crewed lander sinking into unexpectedly soft terrain could shift its center of gravity beyond stability limits, toppling the vehicle and killing the crew inside. Dust kicked up by landing rockets creates contamination risks that Apollo astronauts experienced on the Moon and reported as among their most significant operational challenges. Landing engines direct exhaust plumes toward the surface at high velocities, lifting dust that can coat solar panels, obscure windows, and infiltrate equipment seals. A layer of dust on solar panels reduces power generation. Dust on optical sensors blinds navigation and communication systems. Dust in mechanical seals accelerates wear and creates leak paths. Any of these factors could convert a successful entry into a failed landing. The spacecraft might survive the 7-minute entry sequence perfectly, only to tip over during touchdown or become trapped in soil that cannot support its weight. The mission's defining moment of success might transform into catastrophe in the final seconds. This exposes the core issue that makes Mars surface operations qualitatively different from anything humans have attempted in spaceflight history. The crew has now landed in equipment that has operated continuously for 9 months during transit, endured the violent stresses of atmospheric entry and propulsive landing, and must now function reliably for an extended surface stay before performing flawlessly once more for the return journey. On the lunar missions, the landing module was essentially fresh from the factory when it touched down. The spacecraft had operated for only 3 to 4 days since launch. Its systems had not accumulated radiation damage, thermal stress cycles, or mechanical wear at levels that affected performance. The crew stayed on the surface for hours to days, then departed before equipment degradation could accumulate to dangerous levels. Every piece of Apollo landing equipment was used once, briefly, then abandoned on the lunar surface. The ascent stage lifted off using engines that had never fired before and would never fire again. The descent stage remained on the Moon, with all its potential failure modes irrelevant once the crew departed. Nothing needed to function for extended periods or survive for later reuse. A Mars surface stay would last weeks to months depending on mission architecture, with some proposals extending to over a year during the surface phase. Throughout this period, the crew must live in a habitat that was designed years earlier on Earth by engineers who have never experienced Mars conditions, manufactured by contractors, selected through competitive bidding processes that prioritize cost and schedule alongside technical excellence, tested in facilities that cannot fully simulate the Martian environment, and transported across interplanetary distances while experiencing stresses that ground testing cannot replicate. Surface operations require power generation that exceeds anything robotic Mars missions have demonstrated. The most capable Mars rovers operate on approximately 100 watts of electrical power during peak activity. Human life support systems require kilowatts of continuous power. The habitat demands heating against nighttime temperatures that drop below -70 degrees Celsius. Life support systems must run continuously to maintain breathable atmosphere. Recharging spacesuits for surface expeditions requires significant electrical input. Scientific equipment consumes power during operations. Communication systems need electricity to maintain Earth contact. Solar power on Mars generates approximately 40% of the energy available at Earth's distance from the Sun due to the increased orbital radius. This reduced insolation requires proportionally larger solar arrays to generate equivalent power. But larger arrays have more mass, which adds to the payload that must survive entry and landing. Every square meter of solar panel that reaches the Martian surface required launch vehicle capacity, transit trajectory support, and landing system accommodation. More critically, dust storms can reduce solar input to near zero for weeks at a time during regional weather events, and for months during global dust storms. The global dust storm of 2018 darkened Martian skies across the entire planet for months, blocking sufficient sunlight that the Opportunity rover could not recharge its batteries. After 15 years of successful operations, Opportunity went silent during that storm and never recovered. A crewed mission cannot simply wait out a dust storm in powered-down hibernation, as robotic systems can attempt. Humans need continuous life support regardless of external conditions. The habitat must maintain thermal control to prevent crew from freezing during weeks without solar heating. Water processing must function to maintain hydration supplies. There is no option to shut down and wait for better weather. If solar power fails during an extended dust storm, backup power must activate immediately and sustain full life support operations until solar generation resumes. This backup power requirement adds redundant systems that add mass that must be landed, with all the complexity chains that backup systems create. Nuclear power provides an alternative that does not depend on sunlight, but nuclear solutions introduce their own complexity burdens. Radioisotope thermoelectric generators have powered deep space missions for decades, converting heat from plutonium decay directly into electricity through solid-state thermocouples. RTGs are reliable precisely because they contain no moving parts that can fail. But individual RTGs produce only approximately 100 watts of electrical power, far below human habitation needs that require kilowatts of continuous supply. Nuclear fission reactors can generate kilowatts of electrical power from small packages using controlled chain reactions. The Kilopower project has demonstrated prototype space reactors that might meet Mars surface power requirements. But no space-rated fission reactor has ever been deployed for human life support. Developing Testing and qualifying such a reactor adds another layer of complexity and another chain of failure modes that must be integrated with all other mission systems. Every surface activity introduces dust contamination as a threat that has no Earth-based equivalent of comparable severity. Martian regolith consists of fine particles with angular shapes, created by eons of physical weathering without the liquid water that rounds terrestrial sediment grains. These angular particles cling to surfaces through electrostatic attraction, stronger than lunar dust exhibited. They resist removal through brushing or blowing. More concerning, Martian dust contains perchlorates and other reactive chemicals at concentrations that would be hazardous to human health if inhaled. These oxidizing compounds can damage equipment seals through chemical attack. They can irritate human respiratory systems if dust infiltrates habitat atmospheres. They can degrade mechanical components that depend on specific surface properties maintained during manufacturing. The Apollo astronauts reported lunar dust as one of their most challenging operational problems, despite surface stays measured in hours rather than months. Lunar dust abraded spacesuit joints through mechanical action, reducing suit lifetime and mobility. It obscured helmet visors, limiting visibility for surface activities. It infiltrated every crevice of the lunar module interior, coating equipment and creating irritation when crew members removed their helmets. Martian dust is finer than lunar regolith and more chemically reactive. Surface operations would expose equipment to continuous dust accumulation over weeks or months that ground testing facilities cannot fully simulate. The Mars environmental simulation chambers on Earth can reproduce temperature, pressure, and atmospheric composition. They cannot reproduce the specific particle size distributions, electrostatic properties, and chemical compositions of actual Martian regolith in combination with actual Mars gravity, actual solar radiation, and actual operational activities. Spacesuit maintenance becomes critical during extended surface operations in ways that brief lunar excursions avoided. Current spacesuits are designed for limited extravehicular activity durations, measured in hours per use, not daily use over weeks or months. The suits that astronauts wear for space station spacewalks require extensive maintenance between uses. Joints are inspected for wear. Seals are checked for integrity. Life support backpacks are serviced and recharged. Suit technicians on Earth support this maintenance through procedures developed over decades of operational experience. On Mars, the suits must be maintained by the crew themselves using tools and spare parts brought from Earth, following procedures that may not anticipate every failure mode that actual operations reveal. Joint bearings wear as suits flex through thousands of movement cycles. Seals degrade as dust particles infiltrate and abrade sealing surfaces. Life support backpacks require consumable replacement as carbon dioxide absorbent becomes saturated and batteries lose capacity. A mission must carry sufficient suit maintenance supplies to keep multiple suits operational throughout the surface stay duration. But carrying more supplies means landing more mass, which means larger entry vehicles, which means more propellant, which means larger transit spacecraft, which means more launch capacity required from Earth. Every component connects to every other component through mass relationships that constrain the entire mission architecture. If a suit fails beyond crew repair capability during surface operations, the affected crew member becomes unable to participate in extravehicular activities that define the mission's scientific purpose. Their contribution to surface exploration drops to zero. The remaining suited crew members must absorb additional workload during every surface excursion, increasing their fatigue and error probability. But none of this addresses the deeper problem that looms over every surface activity. The surface phase must conclude with the most demanding single operation of the entire mission, launching from Mars and returning to Earth. The Mars Ascent Vehicle represents engineering requirements that have never been demonstrated in any previous space mission. This spacecraft must survive months of surface operations while maintaining launch-ready status. Unlike Earth launch vehicles that roll out to the pad days before liftoff and receive continuous attention from ground crews, the Mars Ascent Vehicle must sit on an alien surface through temperature cycles, dust accumulation and radiation exposure for the entire surface stay duration. The ascent vehicle must then lift off from a planet where no launch infrastructure exists beyond what the mission brought. No concrete launch pad provides a stable foundation. No service tower allows access for final inspections. No ground crew can perform the thousands of checks that precede terrestrial rocket launches. No abort options are available if systems malfunction during ignition. The crew must trust equipment that has been sitting in harsh conditions for months to perform perfectly when called upon. Launch from Earth involves armies of technicians performing final inspections in the hours before liftoff. Sensors throughout the vehicle continuously report status to mission controllers, who can halt the countdown if any parameter falls outside acceptable limits. Weather conditions receive evaluation because wind and lightning create launch hazards. Range safety officers verify that tracking systems can destroy an errant vehicle before it threatens populated areas. Launch from Mars involves a crew of perhaps 4 to 6 people who have spent months on an alien surface, performing physically and psychologically demanding activities. They must initiate a countdown sequence that they have practiced in simulation but never executed for real. They must verify system status using onboard displays that show what sensors report, which may or may not accurately reflect actual conditions. No external verification is possible. No ground controllers can halt the count. If the ascent engines fail to ignite, the crew sits on Mars with no rescue possible. No repair is possible for catastrophic propulsion failure. They would simply wait until life support consumables expire, knowing that no help can arrive. If the engines ignite but guidance fails, the vehicle departs from its planned trajectory. A small deviation might still reach orbit. A large deviation ends in vehicle breakup or impact with the Martian surface. The crew would experience a few seconds of unexpected acceleration before the end. If the vehicle reaches orbit but cannot rendezvous with the Earth return vehicle waiting there, the crew dies in Mars orbit. They might survive for days or weeks on ascent vehicle consumables, watching the return spacecraft that they cannot reach while waiting for oxygen depletion or carbon dioxide buildup to end their mission. The ascent propellant presents challenges that terrestrial rocket science has never addressed. Chemical rockets require fuel and oxidizer in specific conditions. Correct temperature ranges, correct pressure conditions, correct purity levels, and absence of contamination that could disrupt combustion. Propellants can degrade over time through chemical reactions that alter their properties. Tanks can develop leaks through seal degradation or micrometeorite punctures. Feed systems can clog with particulates that infiltrated during surface operations. A propellant system that tested perfectly on Earth under controlled conditions might fail after 9 months of transit stress, entry heating, surface temperature cycling that ranges over 100 degrees Celsius daily, and dust contamination from months of Martian exposure. The first complete test of the integrated propulsion system under actual conditions would be the launch attempt itself. Some mission architectures propose manufacturing propellant on Mars using in situ resources to reduce the mass that must be delivered from Earth. The Martian atmosphere is 95% carbon dioxide, which can be processed into carbon monoxide and oxygen through chemical reactions. Water ice exists in polar regions and possibly in subsurface deposits at lower latitudes. Chemical processing could theoretically combine carbon and hydrogen from these resources into methane fuel, while separately producing liquid oxygen as oxidizer. In situ, resource utilization sounds elegant in concept. It transforms the mass budget equation by trading Earth-launched propellant for Mars-manufactured propellant, potentially reducing launch requirements by tens of metric tons. Mission studies frequently assume ISRU success in their mass calculations. The practice introduces complexity that those elegant calculations ignore. The processing equipment must be landed on Mars before the crew arrives, potentially years in advance to stockpile propellant before human landing. This equipment must deploy autonomously without crew assistance, operating robotically on an alien surface. It must process atmospheric gases and extracted water through chemical reactors, producing propellant at required purity levels while operating reliably for months or years. Any malfunction in propellant production cascades into ascent vehicle unavailability. If the ISRU system produces insufficient propellant, the ascent vehicle cannot reach orbit. If it produces contaminated propellant, the ascent vehicle may fail during launch. If the system fails entirely, there is no backup propellant source. The crew depends completely on automated equipment that has been operating on Mars for years before their arrival. The processing equipment also requires power from the same solar arrays or nuclear sources that must support crew habitation. It requires maintenance that crew must perform using tools and procedures developed on Earth. It requires quality verification systems that can confirm produced propellants, meet specifications before crew trust their lives to that propellant. Testing propellant quality on Mars requires analytical equipment that adds mass and complexity to surface systems that were already straining against mass budgets. Assuming successful ascent from the Mars surface, the vehicle must rendezvous with the Earth return vehicle waiting in Mars orbit. This orbital mechanics problem resembles Apollo lunar orbit rendezvous, where the ascent stage had to find and dock with the command module that would carry the crew home. But Apollo rendezvous occurred within hours of lunar liftoff, performed by crew members who had spent only days in space. Mars rendezvous would occur after months of surface operations that have physically and mentally degraded the crew. The crew members performing the critical rendezvous maneuvers would have lost bone density and muscle mass. They would have experienced psychological stress from months of confinement and danger. The docking mechanism must function after months of storage in Mars orbit, where the Earth return vehicle has been waiting throughout the surface phase. Thermal cycling, radiation exposure, and micrometeorite bombardment have all affected the docking hardware. The mechanism must work correctly on the first attempt because propellant margins for a second approach may not exist. The transfer of crew and samples between vehicles must complete before ascent. Vehicle consumables expire. The ascent vehicle carries only enough life support for the brief transit from surface to orbit, and the rendezvous operation. Delays in docking or transfer could exhaust these limited supplies, endangering the crew before they can access the fully stocked return vehicle. The return journey exposes the crew to all the same risks that existed during the outward transit, now compounded by equipment that has been operating for 18 months and crew members whose physical capacity has diminished. Life support must function for another 9 months using systems that have already operated for 9 months and endured surface operations between. Every filter, pump, valve and sensor is now well past its demonstrated operational lifetime. Any degradation that occurred during the first half of the mission will continue during the second half. Equipment that showed early warning signs during outward transit will be closer to failure during return. Margins that were comfortable at mission start will be thin or exhausted by the time Earth approach occurs. Earth return atmospheric entry differs from Mars entry in ways that introduce new challenges unique to the mission's final phase. Earth's atmosphere is over 100 times denser than Mars, generating far more heating during re-entry at comparable velocities. The return spacecraft will arrive at Earth, traveling at velocities exceeding 11 kilometers per second, higher than typical low Earth orbit returns that reach only about 8 kilometers per second. The thermal protection system must absorb this entry heating after 3 years of exposure to deep space radiation that embrittles ablative materials, micrometeorite bombardment that may have created surface damage, and material degradation from thermal cycling and chemical processes during transit. The crew must trust their lives to a heat shield that has never been tested under actual return conditions after actual mission durations. Ground testing can approximate the heating environment for a few minutes. It cannot replicate 3 years of accumulated degradation followed by entry heating. The first complete test will be the actual return, with the crew aboard. The mission presents not a single obstacle, but an interconnected web of thousands, each compounding the others at every phase, from launch through return. The homeward journey multiplies every risk factor from the outward trip, because systems have accumulated 18 months of continuous operation while crew physical and mental capacity has diminished under relentless environmental assault. The surface operations that make Mars exploration scientifically valuable also extend mission duration, increase system wear, accumulate radiation exposure, and reduce margins for the return journey. The exploration activities that justify the expense and risk simultaneously undermine the probability of successful mission completion. This paradox cannot be escaped through better engineering alone. It emerges from the fundamental physics of planetary distances that dictate transit times, from chemical propulsion limits that constrain what velocities spacecraft can achieve, and from biological requirements of human beings that demand life support throughout. The mission architecture reflects these physical constraints, not engineering failures. No amount of funding, no surge of political will, no breakthrough in management technique can alter the distances between planets or the energy requirements of interplanetary travel. But even understanding all of this, the mathematics of mission success contain final truths that must be confronted honestly. The weight of reality bears down on Mars mission planning with calculations that engineers understand but promotional materials carefully avoid. Every proposed Mars mission architecture includes a section labeled Risk Mitigation Strategies. These sections describe procedures for handling equipment failures, medical emergencies, and off-nominal situations that might arise during the 900-day mission duration. The documents present decision trees, where specific problems lead to specific responses that resolve the situation and return the mission to nominal operations. A valve fails, so the crew switches to the backup valve. A sensor malfunctions, so the crew cross-checks with redundant sensors. A medical emergency occurs, so the crew follows established treatment protocols. These decision trees represent the greatest fiction in Mars mission planning. The documents create an illusion of completeness. They suggest that engineers have anticipated every possible problem and developed solutions for each contingency. The hundreds of pages of failure mode analysis imply that mission planners have exhaustively mapped the space of things that could go wrong. The procedures give crews and managers confidence that whatever happens, a documented response exists somewhere in the flight rules. A real emergency aboard a Mars spacecraft would not present as a single, isolated problem with a clear solution path appearing in a convenient reference document. Real emergencies cascade. One failure triggers secondary failures that trigger tertiary failures that create conditions no one anticipated. The crew faces not a decision tree, but a decision forest, where every path branches into additional paths faster than human cognition can evaluate options. Consider a scenario that actual Mars mission studies have analyzed in formal risk assessments. A micrometeorite strikes the spacecraft hull during the transit phase, creating a puncture that allows cabin atmosphere to leak into space. The immediate response seems obvious and matches the documented procedure. Locate the puncture and seal it before cabin pressure drops to lethal levels. The crew has trained for this scenario. The patch kits are accessible. The emergency response follows familiar steps, but the micrometeorite did not create only a pressure hull breach. Its impact also damaged a coolant line running near the puncture site inside the spacecraft structure. The thermal management system now leaks coolant into the interstitial space between hull layers, while simultaneously struggling to compensate for thermal imbalance from the breach itself. Coolant loss reduces the system's heat rejection capacity. Electrical components normally cooled by this circulation loop begin overheating within minutes of the impact. The environmental control computer sits downstream of the thermal damage, receiving inadequate cooling as the remaining coolant flows preferentially to higher priority systems. The computer starts experiencing malfunctions as elevated temperatures cause processing errors, timing faults, and intermittent sensor disconnections. This computer manages the life support systems that the crew depends upon for survival, but it is now providing unreliable information about cabin conditions. The crew has minutes to diagnose this cascading failure, while cabin pressure drops and alarms from multiple systems compete for attention. Warning lights illuminate across control panels. Audio alarms sound simultaneously at different frequencies and cadences. Display screens show conflicting information, as some sensors report accurately while others fail or disconnect. They must simultaneously locate and seal the hull breach, while it might be hidden behind equipment panels or insulation, evaluate the thermal system damage that they cannot see directly, determine which computer malfunctions represent actual failures versus which represent sensor errors from damaged electronics, providing incorrect readings, and decide which problems to address first, when all of them are urgent and all of them are getting worse by the second. The flight rules provide guidance for each of these problems individually. The hull breach procedure assumes thermal systems remain functional. The thermal system procedure assumes computer systems provide accurate diagnostics. The computer troubleshooting procedure assumes crews have time for systematic fault isolation. None of the procedures address the combination of all three failures occurring simultaneously and interacting in ways that compound their effects. Mission planners call this scenario abort mode branching. Every potential failure generates a branch point where the mission might continue nominally through successful repair, require modified operations with degraded capability, or face termination if the failure cannot be addressed. Each branch leads to further branches as secondary effects propagate through connected systems. But failures rarely occur in isolation. The systems are too interconnected, the stress is too pervasive, the operational durations too long for clean single-point failures. Multiple simultaneous failures create combinatorial explosions of possible scenarios that exceed human planning capacity, regardless of how many engineers contribute to the analysis. A spacecraft with 1,000 potential failure modes experiences 1,000 possible single failures that must be analyzed and addressed in mission documentation. This analysis is tedious but tractable. Engineers can examine each failure mode, assess its probability and consequences, and develop response procedures. But that same spacecraft also experiences nearly 500,000 possible two-failure combinations, where two things go wrong simultaneously or in rapid succession. Each combination may produce different effects than either failure alone because the systems interact. The documentation requirements multiply beyond practical limits. 3 failure combinations exceed 160 million possibilities. 4 failure combinations reach into the billions. The mathematics of combinatorial explosion guarantee that no analysis can address every possible scenario that the crew might face. Some situations will arise that no document anticipated, no training covered, and no procedure addresses. The crew must improvise responses to situations that no one on Earth ever imagined in their specific details. Their improvisation depends on understanding system interactions that were designed by engineers years before launch. Engineers who have since moved to other projects or retired from the workforce. Improvisation requires physical access to components that may be located behind panels designed for convenient ground servicing, rather than in-flight maintenance by suited crew in cramped quarters. It demands tools and spare parts that someone predicted would be needed, based on failure modes someone else identified during design reviews that occurred years before the mission launched. If the predicted failure modes missed the actual failure mode, the tools and parts may not exist aboard the spacecraft. The crew must then improvise further, adapting available resources to unanticipated needs. Some improvisations will succeed, others will fail. The margin between successful improvisation and catastrophic failure depends on factors that no ground analysis can predict. And here we arrive at the irreducible barrier that cannot be overcome by adding more engineers to the analysis effort. More funding to the development program, or more time to the schedule. The complexity of a Mars mission exceeds human cognitive capacity for complete analysis. No team, regardless of size or expertise, can anticipate all failure modes. No document, regardless of length or detail, can describe all possible scenarios. No training program, regardless of duration or realism, can prepare crews for all contingencies. The testing paradox compounds this fundamental limitation. Engineers cannot validate integrated system performance without testing. But no Earth facility can replicate Mars mission conditions with sufficient fidelity to validate system performance for actual missions. Thermal vacuum chambers simulate space conditions with reasonable accuracy for individual components and small assemblies. They cannot maintain those conditions for 900 days while simultaneously operating complete spacecraft systems with human crews aboard. The chambers test thermal behavior but cannot simultaneously test radiation effects, microgravity fluid dynamics, and operational wear accumulation. Radiation facilities expose components to particle bombardment, matching the space environment with calibrated precision. They cannot simultaneously apply thermal stress cycles, mechanical vibration, and dust contamination. They test radiation tolerance in isolation from the other environmental factors that would be present simultaneously during actual missions. Human factors studies place crews in confinement for months at a time, documenting psychological effects and interpersonal dynamics under conditions resembling long-duration spaceflight. They cannot impose actual isolation, where rescue is impossible if conditions deteriorate. Participants know they can leave if situations become truly intolerable. This knowledge fundamentally alters the psychological experience regardless of how realistic the simulation appears. No facility combines all environmental factors at mission durations with human subjects in actual spacecraft hardware, operating under actual mission protocols. Such a facility would essentially be the mission itself, with all the costs and risks that a mission entails. The only complete test of an integrated Mars mission system would be an actual Mars mission. Previous human spaceflight programs developed capability through incremental testing that validated concepts at progressively larger scales before committing to full missions. Mercury taught NASA how to keep humans alive in space for hours. Gemini extended that capability to days, while demonstrating rendezvous and spacewalk techniques. Apollo built on both programs to achieve lunar missions lasting weeks. The space station extended duration to months and then years. Each program provided learning that informed subsequent designs. Each mission revealed problems that ground testing had missed. Each failure created knowledge that improved subsequent success rates. A Mars mission cannot follow this incremental approach within any reasonable timeline. The interplanetary distance precludes missions of intermediate difficulty that would provide learning without catastrophic risk. There is no Mars equivalent to low Earth orbit, where crews could shake down systems while remaining within emergency return range. There is no Mars equivalent to cislunar space, where problems would allow mission abort within days rather than months. The mission either goes all the way, committing the crew to a 3-year journey with no abort capability after the initial Trans-Mars injection, or it does not go at all. The first crewed Mars mission will test every system under actual conditions for the first time. Any design flaw that emerges from that comprehensive test will manifest with the crew aboard, hundreds of millions of kilometers from any possibility of assistance. Some mission planners have proposed one-way missions that eliminate the return complexity entirely. Volunteers would travel to Mars, knowing they will never come home. They would land, establish a permanent presence, and live out their lives on the Martian surface while subsequent missions deliver supplies and additional colonists. This approach reduces mass requirements by roughly half because no ascent vehicle, no orbital rendezvous systems, and no Earth return propulsion would be needed. The mission architecture simplifies substantially when the destination is permanent rather than temporary. Supply missions could be one-way robotic deliveries, rather than complex crewed operations. But one-way missions do not escape the complexity trap that has dominated this analysis from the beginning. The volunteers still need to survive on Mars indefinitely. They need life support systems that function not for 30 months, but for decades, maintaining breathable atmosphere and potable water until the colonists die of old age or accumulated system failures eventually overcome repair capability. They need medical care across timescales that include age-related decline, chronic disease progression, and accumulating injury effects. They need habitat maintenance as structures degrade over decades of thermal cycling, dust infiltration, and material fatigue. They need psychological support across timeframes that dwarf round-trip mission durations. Facing permanent exile from Earth with no possibility of return regardless of how circumstances change, the complexity shifts rather than disappears. Different systems become critical. Different timescales govern failure analysis, but the fundamental problem remains. Thousands of interdependent systems must function correctly across extended durations in an environment that Earth facilities cannot replicate for testing. One-way missions also face ethical barriers that have prevented serious government consideration despite occasional academic proposals. Sending humans to certain death violates principles that space agencies have operated under since their founding. NASA's charter includes returning astronauts safely to Earth. The agency cannot easily abandon this principle regardless of volunteer willingness. The reputational damage to any organization that abandoned astronauts on Mars, leaving them to die when life support eventually failed, would exceed any scientific benefit the mission might produce. Public reaction to astronaut deaths already generates intense scrutiny and program delays. Public reaction to deliberate abandonment would likely end the responsible organization's human spaceflight activities permanently. Private companies have proposed accepting higher risk tolerances than government programs permit. Entrepreneurial space ventures argue that volunteers accepting known risks should be permitted to take those risks if they provide informed consent. This libertarian approach might enable missions that NASA would never approve under its institutional risk frameworks. But private missions still face the same physics, the same complexity mathematics, and the same fundamental barriers imposed by planetary distances that constrain government programs. SpaceX cannot repeal the rocket equation. Blue Origin cannot eliminate communication delays. No corporate culture makes vacuum breathable or radiation harmless. A commercial Mars mission that experiences fatal crew loss would likely end private human spaceflight for a generation, regardless of how many volunteers remain willing to accept similar risks. The regulatory response to astronaut deaths would impose requirements that small companies cannot meet. The insurance market would collapse as underwriters refuse coverage at any premium. The public backlash would poison political support for spaceflight funding and regulatory accommodation. The risk tolerance that enables aggressive mission timelines also threatens the entire commercial space industry if outcomes prove unfavorable. A single high-profile failure could accomplish what decades of cautious government programs avoided, conclusively demonstrating that Mars is too dangerous for human exploration with current technology. Yet still, the fundamental issue remains unaddressed. No organizational approach, whether government or private, conservative or aggressive, solves the underlying problem that makes Mars missions so difficult. Mars is far away. The minimum distance of 55 million kilometers during favorable oppositions exceeds the Moon's distance by factors of 140. The transit time of 9 months at minimum energy trajectories cannot be shortened without propulsion technologies that do not yet exist and may not exist for decades. The journey is long. 900 days of continuous operation exceeds any previous crewed space mission by factors of 3 to 5. Equipment must function reliably across durations that ground testing cannot validate and operational experience cannot guide. Humans are fragile. The biological requirements for survival in space create system demands that robotic missions avoid entirely. Life support complexity dominates mission architecture in ways that have no equivalent for cargo delivery or instrument operation. Equipment degrades, radiation damages electronics, thermal cycling fatigues materials, mechanical systems wear through repeated operation. Everything gets worse over time, and time is the one resource that Mars missions cannot minimize given current propulsion limitations. Complexity multiplies faster than reliability improves. Every backup system added to address failure modes introduces new failure modes of its own. Every additional capability requires additional mass, power, thermal management, and crew attention. The solution to each problem creates new problems that themselves require solutions. These constraints do not yield to management innovation, corporate culture, government funding increases, or schedule extensions. They emerge from physics, chemistry, and biology. They define the problem space that any Mars mission must navigate, regardless of who attempts it or how they organize the attempt. The popular vision of Mars colonization assumes that the first mission opens a path for subsequent missions that gradually reduce costs and risks through learning and scale effects. This assumption mirrors the history of aviation, where early dangerous flights eventually became routine commercial travel that billions of people experience annually with minimal concern. But aviation benefited from circumstances that Mars exploration cannot replicate. Aircraft operate in atmosphere that provides lift, control authority, and the possibility of emergency landings anywhere along the flight path. A pilot experiencing engine failure can often glide to a survivable landing. A pilot encountering severe weather can divert to alternate destinations. The environment enables graceful degradation rather than catastrophic failure. Early aviation also accepted casualty rates that modern society would find intolerable if proposed for any current transportation mode. Hundreds of pilots died developing aircraft technology through the 1920s and 30s. Test pilots died regularly through the jet age. The learning curve that made commercial aviation safe was paid in human lives over decades of fatal accidents that gradually revealed design flaws and operational hazards. Modern society does not accept similar casualty rates for exploration objectives that lack immediate practical necessity. The value proposition of Mars exploration cannot justify fatality. Probabilities that early aviation routinely accepted, because early aviation was developing practical transportation capability with obvious commercial and military applications. Mars exploration, however scientifically valuable, does not offer equivalent justification for accepting systematic crew losses during capability development. Mars does not offer equivalent learning opportunities to aviation in any case. Every Mars mission is a complete test that either succeeds fully or fails catastrophically. There are no emergency landing fields along the transit route, where crews experiencing equipment problems could set down for repairs. There is no rescue capability for crews in distress during any mission phase. The nearest help is months away at best, years away at worst. The learning from failures would come at the cost of lives that modern societies have demonstrated. They are not willing to sacrifice for exploration objectives, however inspiring those objectives may be. Public tolerance for astronaut deaths has declined substantially since the Apollo era, when fatalities were accepted as the price of Cold War competition. The Columbia and Challenger disasters each produced years of program disruption, despite occurring in low Earth orbit rather than deep space. This ethical constraint represents a fundamental difference between robotic and human Mars exploration. Robots can fail without tragedy. The Curiosity rover landing sequence carried substantial uncertainty, given the novel sky crane system that had never been tested under actual Mars conditions. Engineers acknowledged significant probability of failure. Mission planners accepted this risk because the consequences of failure were limited to lost equipment and scientific opportunity, not lost human lives. If the landing had failed, NASA would have lost a $2.5 billion investment and years of development effort. They would not have killed anyone. The next mission could incorporate whatever lessons the failure revealed and try again with improved designs. Human missions cannot operate with 30% failure probabilities under any institutional framework that currently governs spaceflight operations. The Space Shuttle program accepted per mission loss probabilities around 1% based on operational experience, and this risk level produced 2 fatal accidents across 135 missions that killed 14 crew members. The public and political response to those accidents disrupted the program for years after each occurrence. Modern risk acceptance standards require mission success, probabilities exceeding 95% for crewed operations, with some analysts arguing that interplanetary missions demand 99% success probability given the impossibility of rescue and the extended public attention such missions would receive. Achieving these reliability levels with Mars mission complexity may be mathematically impossible using any technology that currently exists or that could reasonably be developed within the coming decades. The mathematics are straightforward. And unforgiving. A mission requiring 1,000 systems, each with 99% individual reliability, produces compound mission reliability below 1/100%, meaning virtual certainty of at least one system failure somewhere in the architecture. Even 99.9% individual reliability across 1,000 systems produces only approximately 37% compound mission reliability, meaning nearly 2/3 probability of at least one failure. Reaching 95% mission reliability with 1,000 systems requires each system to demonstrate 99.995% individual reliability across 900 days, a performance level that has never been demonstrated for complex equipment operating in the space environment for any duration. This conclusion does not reflect engineering pessimism or institutional timidity. It reflects honest assessment of the gap between promotional materials produced by organizations competing for funding and public attention versus the physical constraints that any actual mission must satisfy, regardless of how much enthusiasm its proponents generate. The Mars missions described in press releases, conference presentations, and animated videos bear little resemblance to missions that physics and biology would actually permit with current or near-term technology. The videos show crews floating serenely through spacious modules, touching down gently on Martian terrain, exploring the surface in flexible suits, and returning home to celebrations. The reality would involve exhausted crews struggling to maintain degrading systems, landing through sequences that offer no margin for error, exploring in cumbersome suits that limit mobility, and attempting returns in equipment that has been operating far beyond its validated lifetime. A real human mission to Mars with a planned return to Earth would require simultaneous breakthroughs in multiple technology areas that currently remain at basic research stages. It would require life support systems that function reliably for 3 years without resupply deliveries or significant maintenance beyond crew capability, achieving reliability levels that the International Space Station has never demonstrated despite continuous resupply and regular equipment replacement. It would require propulsion systems that reduce transit time to levels that human physiology and psychology can tolerate without permanent damage, cutting the 9-month minimum energy trajectory to durations that limit bone loss, muscle atrophy, radiation exposure, and psychological deterioration to acceptable levels. No such propulsion system exists beyond conceptual design studies. It would require radiation shielding that protects crews from galactic cosmic rays and solar particle events without adding mass that exceeds propulsion capability, solving a fundamental physics problem that has defied decades of research into lightweight shielding materials. It would require landing systems that can deliver human-scale payloads of 40 to 60 metric tons to the Martian surface, exceeding current demonstrated capability by factors of 40 or more, using entry and descent techniques that have never been integrated into functioning vehicles. It would require ascent vehicles that function perfectly after months of surface operations in an alien environment, launching from a planet with no infrastructure, no ground support, and no abort options if systems malfunction during the single opportunity for ignition. Each of these requirements represents a research and development program spanning decades of work before flight demonstration becomes feasible. The integrated system that combines all of them represents challenges that compound beyond the sum of individual component difficulties. Integration creates new problems that individual technology development cannot anticipate. We are not on the verge of Mars mission capability, despite decades of announcements suggesting imminent breakthrough. We are at the beginning of research programs that might eventually produce the necessary technologies for missions that would actually succeed. This assessment may seem discouraging to those who grew up watching Mars landing animations and assuming they would live to see human bootprints in Martian soil. Science fiction has portrayed Mars missions for over a century. Space agencies have announced Mars mission timelines for over 50 years. The gap between vision and reality can feel like a betrayal of dreams that institutions have encouraged across generations, but honest assessment also enables productive focus that fantasy obscures, resources directed toward actual technology development that addresses identified barriers produce more progress than resources directed toward promotional campaigns for missions that cannot yet occur. Understanding real constraints allows realistic planning that produces incremental capability rather than perpetual disappointment when ambitious schedule dates inevitably slip. The cosmos remains as inspiring as it ever was, regardless of human capability to explore it. Mars continues orbiting the Sun, presenting the same scientific mysteries that have motivated exploration proposals for decades. Ancient river channels suggest liquid water once flowed across the surface. Seasonal methane variations hint at processes that might be geological or might be biological. Polar ice caps and subsurface water deposits offer resources that future missions might utilize. The questions that Mars presents to science remain compelling, even when the answers remain beyond current reach. The desire to send human explorers to another world reflects something profound about our species that deserves respect, even when current capabilities fall short of current ambitions. Humans have always looked beyond their immediate circumstances toward horizons they could not yet reach. This yearning drove exploration across oceans, mountains, and eventually into space itself. Mars represents the next horizon in a progression that may eventually span the solar system and beyond. What a real mission to Mars would actually look like, with current technology applied honestly, is a mission we cannot yet build. The complexity required to keep humans alive for 3 years in deep space, land them on another planet, support their surface operations, and return them safely to Earth exceeds our current engineering capacity by margins that promotional videos carefully avoid mentioning, because those margins undermine the funding appeals that sustain institutional interest. This is not a failure of imagination or will. Engineers have imagined Mars missions in extraordinary detail for over half a century. Political leaders have repeatedly declared Mars exploration as a national priority. The imagination and will exist in abundance. What does not exist is the technology to translate imagination into hardware that would actually work. The mathematics of reliability, the physics of interplanetary distance, and the biology of human bodies combine to create requirements that no amount of funding or determination can currently satisfy. Money cannot purchase breakthroughs that research has not yet achieved. Willpower cannot override physics that limits what chemical propulsion can accomplish. Determination cannot keep equipment functioning beyond its validated operational lifetime. The dream of Mars remains as vivid and compelling as it has been for generations. But the timeline for achieving that dream extends further than most people want to hear, and further than most institutions want to admit, because admissions of difficulty threaten the funding streams that sustain organizational existence. The honest acknowledgement of this gap, the clear-eyed recognition of what we cannot yet do despite what we wish we could do, represents the first step toward eventually closing it. Progress requires understanding the actual distance to the goal, rather than pretending the goal is closer than it actually sits. Human ambition has always exceeded immediate capability. Our ancestors dreamed of flight for millennia before the Wright brothers achieved it at Kitty Hawk. They imagined traveling to the moon for centuries before Apollo astronauts walked on the lunar surface. The gap between dream and reality eventually closed through sustained effort, incremental progress, and honest assessment of remaining challenges that guided research toward the problems that actually needed solving. Mars will likely follow the same pattern on timescales that exceed individual human lifetimes and political attention spans. Future generations may accomplish what current generations can only imagine. They will build on foundations that current research establishes. They will solve problems that current engineers can identify but cannot yet resolve. The real mission to Mars begins not with a rocket launch, but with accepting that we are further from launch than we want to believe. From that honest foundation, from that sober recognition of current limitations, actual progress becomes possible, because resources flow toward real problems rather than promotional spectacles. The complexity explosion that has dominated this analysis is not a temporary obstacle that clever engineering will soon overcome. It is a fundamental characteristic of the challenge that emerges from the intersection of physics, biology, and distance. The realism that acknowledges this complexity destroys the popular fantasy of a clean Mars mission launched within any currently living generation, but it also points toward the actual work that might eventually make such missions possible. Until then, Mars continues its eternal orbit, rust-colored and silent, waiting for a species that dreamed of reaching it to finally develop the capability to survive the journey there and back. The planet does not care about human timelines or institutional pressures. It simply exists, presenting challenges that we may or may not eventually prove capable of meeting. The weight of reality is heavy, but reality is the only foundation on which actual achievement can be built.